any symmetry generator, it's always where this means that you have to know how X transforms under MMN. I wrote down something stupid. I wrote down something like delta L, delta L, delta X dot M with N. So that was just wrong. Okay. So, for example, under a Lorentz transformation, this is going to be something like delta MP XN minus delta NP XM. So combining that with this gives you okay, so sorry about that mistake. Okay. Okay, so today, any questions about previous classes? Yes?
So the supersymmetry transformation is continuous symmetry of the action, right?
So the question is if the supersymmetry transformation is a continuous symmetry of the action. Yes, it's a continuous global symmetry. Yes?
So it has a conserved quantity associated.
Yes?
So can you elaborate the conserved quantity?
Yep, we can do the same computation. So, so we have delta L. So remember the Lagrangian. Let's just do the part without the electromagnetic background. So we had X dot P, M, it was a factor of 2. So something like this. So we can compute it. So you have DL. So we just use the same formula. Of course, there's also contribution from the psi's. Delta psi P. In this case, delta of X is just psi. I don't know if it was I psi or psi. And delta psi was X dot, right? So that means this thing is just going to be equal to, so DL, D of the Lagrangian with respect to X dot. So that just gives me something like M over 2. So this is BQ. Is M over 2 X dot P. And then the change in XP is just psi P. And then the other term is DL d psi dot, which is just psi. So you get psi P. And then delta psi P was equal to something like IX dot, right? So there was an I coming from here. And there's probably, the two should add in any case. So I'm not promising the signs. But so this is going to just going to be M X dot P psi P. So that's the generator of supersymmetry for the case that I did yesterday.
So that's why we impose that constraint on the...
That's correct. That's related to that constraint. Any other questions? So another way to get this, which you actually saw if you did the exercise, is that if you see how the Lagrangian changes under Q, it changes by a total derivative. It's the total derivative of this object. So that's another way to see how you get this. Okay, so yesterday was about spin 1/2 using the language of quantum mechanics. Today we're going to do spinors in the language of four-dimensional field theory. Okay, so spinors are different in different dimensions, as Ricardo mentioned. They're not so different, but let's do 4 dimensions before we discuss other dimensions. Okay, so today we'll do D equals 4 spinors. So the starting point is something that maybe some of you have already seen, which is a nice way to describe a vector, which is a 2x2 matrix. So the way you describe it is, so I'll try to use the notation in my notes. So everything I say today is, I think, in my notes, Introduction to Supersymmetry, which is in the reading reading list. So of course, the notes have a whole semester of information, but what I'm going to say today is, I guess, in just the first chapter. So, so I'm going to just define this 2 by 2 matrix in this way. I guess minus I. So the nice feature of this is that if you take the determinant of this matrix, so let's call this matrix capital X, I'll just write it like this. It's just equal to minus x0 squared, I guess plus x0 squared. Which is just equal to A to Mn. So the determinant of this matrix is the Lorentz invariant object. So you can ask, what transformations of this matrix will preserve the fact that you want this to be preserved under Lorentz transformation? Okay? So that's easy. It's just if X is acting this way, where M is any 2 by 2 matrix, and M dagger is any 2 by 2 matrix, where these matrices have determinant 1, then it's easy to see that this object will still have determinant, the same determinant as before, right? Because the determinant is the product of all of these. And furthermore, you can easily see that this matrix is Hermitian, right? And obviously, this is also Hermitian, because if I take the Hermitian conjugate of this, and X is Hermitian, it's also Hermitian. So you can, of course, M is going to transform the X's. It's not going to leave the matrix invariant, but it's going to leave the determinant invariant. So this is a Lorentz transformation. I don't know how you learned about Lorentz transformations, but in all the textbooks I know, the Lorentz transformation is defined as transformations, linear transformations of X, which preserve this. Okay. Okay, so these M's, normally you define the Lorentz group as being SO31, right? So SO31 are the objects, essentially the 3 is because there are 3 minus signs here and 1 plus sign. That's why it's 3, 1. If they were all plus signs, you would call it SO4, not SO3, 1. So M is a 2 by 2 complex matrix with determinant 1 that has a name. So it turns out we call it SL2C. So it's called, C is because it's a 2 by 2 matrix which takes values in complex numbers. And S is because it has determinant 1. Okay, so this S is the same S as this S. Now, how many degrees of freedom does it have? So M, of course, it's a 2 by 2 complex matrix. It has 4 complex parameters, but the determinant is 1. So that means it has 3 complex parameters. Okay? 3 complex parameters are, of course, 6 real parameters, which is, of course, the same as SO31. You have the 3 rotations and the 3 boosts. So an alternative way of defining Lorentz transformations is using matrices which take values in SL2C. Okay? And, of course, the two are related. Any rotation or boost can also be described as this matrix. Okay, so the relation is a little bit non-trivial, but the easiest way to describe the relation is by introducing these Pauli matrices. So you've probably already seen 3 of the Pauli matrices in your quantum mechanics course. But you add this other one, sigma 0, it's convenient. what do these matrices have the property? That they're all Hermitian. And at least these three are traceless. Okay, this one, of course, is not traceless. It's proportional to the identity. Okay, so these M's, if you remember about defining the determinant, if you define M as the exponential of something, so this is a 2 by 2 complex matrix, which means let's call sigma j. Let's call this lambda j. Then if these Pauli matrices are traceless, so these are 2 by 2 matrices, these are just parameters. If these are traceless, then this will have determinant 1. Right? You should have, it's not difficult to prove. The easiest way to prove it is if you think of this as diagonal. And then you can see that if the product of the diagonal matrices are 1, that's, of course, comes if the trace of these matrices is 0, because when you exponent 0, you get 1. Okay? If it's not diagonal, it's slightly more complicated, but that's the idea. Okay? So that means we can parameterize M in terms of these lambdas and these Pauli matrices. But of course, the lambdas can be complex. Okay, so if you want, you can split it up into a real part and a complex part. So let's call it lambda plus I omega. So you have 3 complex parameters here. And these lambdas and omegas just are related to the rotations and boosts. Okay, so you can do a rotation around the x-axis, a boost in the x direction, and that would be omega 1 and lambda 1 and omega 1. Okay. Or you could do a rotation around the y-axis and a boost in the y direction, and that would be related to lambda 2 and omega 2, etc. And of course, M dagger is just e to the minus I sigma j lambda minus I omega. Okay, because I just take the Hermitian conjugate of this. Okay, any questions? So I'm not changing anything. I'm just describing my parameters of my boosts and rotations using this 2 by 2 complex matrix. This is, of course, special to 4 dimensions. Okay? We're not going to do this in any dimension. Okay, so now I can tell you what a vector, a spinner, those things are. So I can define a spinner as something which either transforms by action of M or of M dagger, whereas a vector involves a transformation using M and M dagger. So I'm going to put in some indices now. So these are, of course, 2 by 2 matrices. I'm going to use, let me try to use this notation, AA dot. So why do I put a dot on one of the A's and an undotted on the other end? Because I'm going to think of this object in which M carries undotted indices, so let's call it AB. So this would be BB dot. And M dagger carries dotted indices. So this would be XAA dot. It's a 2 by 2 matrix. So the first entry is without a dot, the second entry is with a dot. Okay, so I'm going to distinguish the two. That's going to be important. And M is going to carry just the undotted indices, and M dagger will carry just the dotted indices. So in some sense, you can think of the dotted indices as being the complex conjugate of an undotted index. So every time I see a vector is something with, everybody knows how a vector transforms under Lorentz transformations. I convert it into a 2 by 2 matrix, and the conversion is simple. It's just xm is equal to xaa dot sigma m aa dot, where these Pauli matrices are defined here. And here's my definition of the x's. Now, when you work in Minkowski space, you know that you can raise and lower indices using A to mn. Okay, what about these indices? So these indices, of course, they go from 1 to 2, and you raise and lower using epsilon tensor. So epsilon tensor, in this case, will just have 2 indices, and since A and B go from 1 to 2, it's just defined to be epsilon 1, 2 is equal to minus epsilon 2, 1 is equal to 1. I think that's the, I don't remember the convention I use, but it doesn't really matter. And you also can lower indices. So in that case, it's convenient to define the opposite way. Epsilon 2, 1 is equal to minus epsilon 1, 2 is equal to 1. And of course, epsilon 1, 1 equals epsilon 2, 2 equals 0. So it turns out that this object, just like A to mn is preserved under SO31 transformations, that's why it's a constant, that's why the Minkowski metric is invariant under SO31. Epsilon AB is invariant under SL2C. So you can think of it as a metric for SL2C if you want. But you can also think of it just a tensor which allows you to raise and lower indices. So of course here I have some raised indices and some lower indices. And X also, here I had up index, here I have down index. So I have to say how to relate them, right? So if it was vector, I of course know that xm is equal to A to mn xn. Now I can write the same type of relation with these dotted and undotted indices using epsilon to raise and lower. Okay, so you can say xaa dot is equal to epsilon AB, epsilon A dot B dot, xbb dot. So again, it's just indices which I can raise and lower. Okay. Now it's also convenient to define these matrices with upper indices instead of lower indices. So again, you can use epsilon to raise and lower them. So normally people call this sigma bar for a reason that's not clear to me, but so sigma bar m aa dot is equal to sigma m bb dot, bb dot, epsilon ab, epsilon a dot b dot. And you can compute it, of course, using these definitions here. And now I should really make sure I'm using the same signs, otherwise I'll get confused later. Okay, that's right. So this turns out to be equal to minus omega bar A dot. And this is equal to plus omega bar 0 A dot. So if you compute this matrix and m equals 0, you turn out to get the same thing as before. Whereas if you compute these, you turn out to get the minus sign. So again, this is just a definition, okay? But it's convenient to have these two types of matrices because we're going to have to take the product of these and then you're going to have to contract an upper and a lower index, so it's convenient. Okay? Normally one puts the first index is dotted here. I should have done that here too, sorry. Sorry about that. So of course it makes a difference because it's row and column, so it depends which one you go Okay, so those are the Pauli matrices. Go ahead. So M goes from 0 to 3, right? So there are 4 independent components. And A and A dot go from 1 to 2. So it just means the first index is just the row and the second index is the column. So this is x11 dot, this is x12 dot, this is x21 dot, this is x22 dot. Okay? So it's just a reshuffling of the coordinates. Other questions? So if you are lost now, you will be lost for the rest of the lecture. Okay? Because spinors, obviously, otherwise I wouldn't have discussed all this, are things which carry these kinds of indices but don't carry the vector indices. So spinor has a single index, A, or psi bar would carry a single index, A dot. Just so you, I don't want to confuse you now, but Ricardo has been using a different notation in which the spinor has 4 components. So probably he didn't even tell you what it was, but psi alpha turns out to be related to psi A. So his alpha had 4 components. And they're related to these in this way. But it's much simpler, I guarantee you, although 90% of the literature uses this notation and 10% uses this. The 10% uses the right notation. So it's historical, and as soon as you try to work with these, you'll see that using this notation, you will never get lost, whereas using this notation, you will always get lost. Okay, any case, so I'm going to discuss, at the end of the lecture, maybe I'll say the relation, but so how do these things transform under Lorentz transformations? Well, it doesn't take much guesswork. So this is going to be MAB, psi B. And this one, it's better, normally one does it from the other side. So psi B dot, M, I think I called it M dagger, B dot, A dot. So this is how psi and psi bar transform. So, what can I say? You know that the Lorentz transformations are encoded in these matrices, so it just tells you how, when you do a rotation or a boost, how it affects the psi and psi bar. So using this, so this is completely explicit, right? Matrices, parameters. If I tell you a rotation, I can tell you how psi and psi bar transform. Now you can try to construct Lorentz invariant objects or kinetic terms for the spinors or whatever you want to do. Okay? At the moment, these are anything. I didn't tell you these are fermionic. Okay? They're spinors. So you have to distinguish in your mind a spinor is something that transforms under Lorentz transformations. A fermion is something which is anti-commuting. An electron is both. It's a fermion and a spinor. But you could have something which is a spinor which is not fermionic and vice versa. So this has nothing to do with anti-commuting commuting. It's just a representation of the Lorentz group. Okay, any questions? Okay, I suspect there are questions, but people don't want to ask. So, go ahead, yes?
You said that the boosts gamma and omega are related to boosts and to...
Yes?
Which one is related to the boost? Which one is related to rotation?
So this is the rotations, and these are the boosts. So the rotations always have an I in front, whereas the boosts would not have an I in front. Other questions? Yeah? Yes? Yes, but I told you these are Hermitian, remember? So I use that property. But it's a good question. Any other questions? Okay, so epsilon is an antisymmetric tensor where A and B go from 1 to 2. So it's a 2 by 2 antisymmetric matrix, which is just, I guess the way I'm defining it's 1, minus 1, 0. So this is what's up in this. Epsilon AB is this. Okay. So it's Levy-Chivit tensor. I don't know if that helps you, but it's just an antisymmetric tensor. No, it can do anything. So for example, if this is something with an upper index, I can also define something with a lower index. So for example, I can write this as epsilon BA psi A. So it can also raise and lower indices of anything, not just Pauli matrices. Other questions? Go ahead, you first.
I was wondering if in the expression from the Pauli matrix relation, you just put them in components, maybe it would be possible when operating to exchange the places, or?
Are you asking how to compute this? I can compute it for you right now if you want.
No, not exactly, but if it's possible, exchange the places between the epsilons and...
So the epsilons are just numbers. So numbers means, and just to not confusing, they're bosons, they're just ordinary numbers. Everything here is just ordinary numbers. So you could put the epsilons here if you want. Doesn't matter where you put them. I'm not sure what you mean components. So A and B go from 1 to 2. So this is epsilon, for example. Let's do this. I think it'll be clearer if I do it. So let's compute sigma bar 0, the matrix AA dot. Okay? So this is of course equal to sigma bar 0, 1, 1 dot, sigma bar 0, 1, 2 dot, sigma bar 0, 2, 1 dot, sigma bar 0, 2, 2 dot. Right? Okay, this is equal to, let's do 1, 1 dot first. So this is equal to sigma, just using this definition, it's equal to sigma 0 BB dot epsilon 1B dot 1B epsilon 1 dot B dot, right? But this epsilon is only non-zero if the first element is 1, this has to be 2. So the only thing that can contribute here is sigma 0 2 2 dot epsilon 1 2 epsilon 1 dot 2 dot. Right? Epsilon 1 2 is 1. Epsilon, I didn't tell you the dot. The dotted one is the same. Epsilon A dot B dot is the same. It's epsilon 1 dot 2 dot equals epsilon. It's the same. So this is just going to give you 1. Epsilon 0 2 2 dot, I read that off from here, minus 1. So the answer is equal to minus 1. You do for the next one, you'll find it's 0, this is minus 1. So we find that this matrix here is the same as this matrix here. Okay. You can do the other ones in the same way. And actually, I made a mistake because I said this should have been the first one. So sorry about that. But it's the same, just because obviously these are 0, so it didn't matter which I... Okay, so we can compute the others in the same way. Okay. There was another question? Yes?
When you map vectors to covectors in a metric space
Yes?
using the metric,
Yes?
have a isomorphism, that's usually called musical isomorphism.
I don't know that phrase. It's called what? Okay, it's possible, but I don't know the phrase. But what are you trying to ask?
When you like lower and raise
Yes.
index with tensors and
Yes.
vectors and covectors,
Yes.
this kind of mapping between vectors
Yes,
with the metric is called use homosymmetry.
okay.
And what is the name of this isomorphism?
You lost me. I don't know. I'm sorry. I don't know the name. So it's possible there's a name, but I didn't even recognize the name of the first one you said. So obviously, I don't know the answer to the second one. But yes, yes, psi bar. Yes. Oh, okay. Good. Very good question. So very easy also. So psi 1 dagger is psi bar 1 dot. Psi do dagger is psi bar 2 dot. Other question? It's almost the only thing you can do because you know that M is the Hermitian conjugate of M dagger. So it has to switch the undotted with the dotted indices. Those. I understand what you're saying, and that's using this 4-component notation that I told you you should not use. So, okay, go ahead next. Okay. So now we can start to think about what these psi's represent. So the minimal representation you have is with these psi with 2 of these indices, 2 of A dot. So this is called chiral spinner. This is called an anti-chiral spinner. So in 4 dimensions, this is the smallest representation you can have. So it has 2 complex components. Okay. Now you can have more of them. So this is sometimes called Majorana representation. You can have twice as many. It's called Dirac representation. But it's just words. So everything is made out of these. And now the next thing is to get physics out. So we want to say, let's see, how do we describe, for example, kinetic term for these objects? Okay. Maybe before I say that, let me say something more general, which I'm not going to use. But we already saw that a vector can be described as something which has a single A and a single A dot index. So what are the representations we've seen so far? So we have psi A, we have psi bar A dot. You can also have something with, so this would be a vector, right? This would be chiral spinner, anti-chiral spinner. Of course, you can also have something with no indices. Let's call it phi. So this is scalar, you call it. Anti-chiral spinner. Well, you could also have something with, for example, 2 of these indices. So you could have something like phi AB. But if it has 2 undotted indices, remember that you have epsilon AB. So this actually decomposes into something proportional to epsilon AB, which is just epsilon AB times a scalar, plus a term which is symmetric. So the antisymmetric part is proportional to epsilon AB. You can also have the symmetric part. So normally, people write the symmetric part by putting parentheses around it. So you can think of this as phi AB plus phi BA, maybe with a factor of a half, depending on your convention. Okay? So let's put a half here. So phi, if there was no, so this thing has 4 independent degrees of freedom because A and B go from 1 to 2, but one of them is antisymmetric. So this object, instead of having 4 degrees of freedom, this has only 3 degrees of freedom. Right? So let me put the number of degrees of freedom here. So you have 1, it says 2, 2, it says 4, 3. And you could also have other things. So let me write it like this to remind you that it's symmetric. You could also have things like psi AB A dot. 2 undotted, 1 dotted. Now, why am I calling this a psi and this a phi? Because if these corresponded to physical particles, there is a relation between the statistics and the number of indices. So this would be a boson, these would be fermions. So anything with an even number of these is a boson, and anything with an odd number is a fermion. And of course, you could have the complex conjugate of this. Could be something A dot B dot A. So this has 3 degrees of freedom. How many degrees of freedom does this have? Somebody want to guess? So it has 6, because it's 3 from here, but then you have 2 of these, so this would have 6. And similarly, this would have 6, so this would be the complex conjugate of it. So it turns out all the representations of the Lorentz group can be described in terms of just these objects. So it's either, in general, the most general thing you can write down is something which has n chiral indices and let's call M or P antichiral indices. So normally one defines the spin of this object. So this is, now you have a definition of spin. So the spin turns out to be the number of these indices divided by 2 plus the number of these indices divided by 2. And in fact, it's normal to think of these are independent representations, so it's better to think of the thing like this. Okay? And the total spin is just the sum of these. So this would have spin 0, 0. This would have 1/2, 0. This would be 0, 1/2. This one would be 1/2, 1/2. So we call it spin 1, but actually it's more accurate to call it spin 1/2, 1/2, because this also is spin 1. But this is 1, 0. And I forgot one. You could also have phi, A dot B dot. You could also have this one. That's another one. That would be 0, 1. These turn out to be 1, 1/2, right? Because I have 2 of these. So these are spin 1. This is spin 1, spin 1, spin 1, but different kinds of spin 1. And this is spin 3/2. Okay? And you could do spin 2, et cetera, et cetera. Go ahead, question? Yes? Good. Why this is 6? Because this one, you understand why it's 3? Okay, so but it has an extra index, and the extra index has 2 components. So it's 3 times 2. Okay. Yes, go ahead. What is, sorry, B dot. Sorry about that. I got carried away. Yes? Times chiral. Times or plus? Okay. Okay. So normally the question would be if you multiply, if you have psi times psi bar, so that would be like this object. So this would have 4. So if you multiply one representation by another, you get the product of the sizes of the representation. You can't really add different representations. It's like adding apples and oranges. It doesn't make sense. You can't add, but you can multiply them. No, they're independent. They're independent representations. Okay, so this is, of course, mathematics. And now we're going to do physics. So, of course, the reason why this is interesting is because they're particles which transform like this. Okay, so let's start to write down actions, which you've already seen in Ricardo's lectures, but using a different notation, which I think is much more complicated. So So let's write down a kinetic term. Okay, so the kinetic term we're going to write down is, for example, psi A, sigma m a dot, dm psi A. So this, you saw something like this in, I don't remember if you used, what notation you used, but you probably used these gamma matrices, okay? So he made a statement at one point that the gamma matrix depends on the representation, what it looks like in terms of the, so now I can tell you what it is in terms of these. So gamma m alpha beta. A dot. So in a certain representation, which I think is called Weil representation, this is the way the gamma matrix is related to the Pauli matrix. So if you just decompose what he wrote down in terms of what we're writing down, this is the action you get. And I think there's a factor of I, probably. So, and then you can also write a mass term. So this would correspond to the case in which the fermion is massless. And the mass term you're going to add is something like this, minus I m over 2. It's essentially the only thing you can write down, which is Hermitian. So now this turns out to, in his language, would be a Majorana. So I don't think he's described the difference between Majorana and Dirac. But there are different representations. And if this psi is the complex conjugate of psi bar, then it's called Majorana. Just to tell you what Dirac is, so this would be Majorana. If you're doing Dirac, then you actually need two of them. So you call one of them chi and one of them psi. And then you have two terms. You have this term plus I chi bar A dot. So this would be called, and there's a mass term also. This would be called Dirac. So it turns out the electron is in the Dirac representation. Why? Because it's the anti-electron is a positron. It's a different particle. In other words, the electron carries electric charge. There are other types of fermions you can think of writing down which don't carry charge, which are real. So in that case, it would be called Majorana. Okay, so what are some properties of this action? So we can, of course, easily compute the equation of motion. So if we vary with respect to psi bar, we'll get the equation like this. I sigma m a dot dm psi a minus, so you have a, so I'm varying with respect to psi bar. So I'm going to get this term from here, and from here I'm going to get a plus I m, factor of 2 cancels because I have 2 of these. So it's going to be something like psi bar a dot. So this has to be equal 0. So this is the equation of motion you get by varying with respect to psi bar. And of course, you can vary with respect to psi, and you'll get the complex conjugate of this. So what you find is that psi bar is actually related to the derivative of psi, which means on shell, or using the equation of motion, the two are not independent. Now that's important because what you want to know is how many physical states are described by psi. So for example, electromagnetism, I think you know, you have AM of x, which has 4 degrees of freedom, but there's a gauge symmetry, and there's also an equation of motion which kills 1, so a photon only has 2 degrees of freedom and not 4. Now it turns out this spinner, the spinner we decided, the Majorana spinner has 2 complex degrees of freedom. But we just found out that the 2 complex degrees of freedom are related to each other. If you know what psi A is, you know what psi bar A dot is. So in fact, there's only 2 physical degrees of freedom. Physical means on shell or using equation of motion. Well, I told you that this is not the electron. The electron is here. Why? Because an electron has 2 degrees of freedom. It can be spin up or spin down. But the positron also has 2 degrees of freedom. It can spin up or spin down. So there are actually 4 degrees of freedom described by an electron. That's why you need to have chi and psi. So this action here only describes 2 degrees of freedom, whereas this one describes 4 physical degrees of freedom. Okay, that's going to be important when we describe in the next lecture supersymmetry, because supersymmetry, if I have 2 bosonic degrees of freedom, I need 2 fermionic. So for example, if I ask what's the superpartner for the photon, photon is this object here, which has 2 physical degrees of freedom, it has to be Majorana, because it only has 2 degrees of freedom. Okay. So the photino would not be like the electron. It would be something without charge. Okay, any questions? Go ahead. You first, and you go ahead. Why did I switch I put the A before the A dot? Is that the question? So that's just a convention, but I'm just defining my matrix so that the first index is always undotted and the second index is dotted. I could have written this in a different way, which probably would have made you happier. If I switch the order of these, and I switch the sign, so these are fermions, right? So if I switch the order, I have to put a minus sign. So this would be equal to minus I dm psi A psi bar A dot. So I could have written it this way. If that, I don't know if that makes you happier because these indices are close to that. Okay. Yes? Okay, so vial is just another word for chiral. Okay, go ahead. There was another question. Yeah. Okay. So it's going to be psi A chi A. I don't remember if it's plus or I could probably figure out. I think it's psi bar A dot chi bar. No, I'm not sure. 1 second. So there are 2 possibilities here. And now I have to remember. So I want the equation of motion. So there are 2 possibilities. It could be that, or it could be psi A, 2 copies of this. 1 second. I think it's this one. I will check it for you, but I think it's this. So that the equation of motion is that this is equal to chi. So you see, when I vary psi bar, if I vary chi bar here, I will get this equation. I will check it, but I'm pretty sure it's this. Any other questions? Okay, so why does this imply that, for example, the mass squared of psi is equal to p squared? Okay, so this equation here you can think of as the square root of the Klein-Gordon equation. So if I do this twice, so let me just show that. So if I take if I act with this equation by this matrix here with another derivative, then what's going to happen is when you act on the first term, it's going to give you box. So if I act with this on this equation, I'm not going to try to do the computation here, but you're going to get something like box psi A coming from here, because you have two derivatives. You have a derivative from here and a derivative from here. And depending on how these indices are contracted, you'll get the box. And then from here, you're going to get this acting on chi bar. But that equation comes from just taking the equation of motion by varying psi. So what you'll find is that this is just going to equal to, you'll get an m squared, so in the end it's going to give you something like this. So this acting on this equation is going to give you 0. So that's why this Dirac equation implies that the mass squared of psi is equal to p squared of psi. So I just wanted to say why this Lagrangian is the correct Lagrangian, okay, at least for the free case. Okay, any questions about what I've said up to now? So one thing I didn't show you is that this Lagrangian is Lorentz invariant, but it's kind of obvious. It just comes from these transformations here. This, I think, Ricardo already said a little bit about. You just have to transform the indices. So you could have asked the same question as when people write down a Lorentz invariant expression, for example, x dot m. How do I know that this is Lorentz invariant? So you say, well, because the indices are contracted, that's why it's Lorentz invariant. So why does contracting indices mean it's Lorentz invariant? Well, then you go back and remember that the Minkowski metric is invariant under the SO3-1 transformation, so as soon as you contract indices, you know it's Lorentz invariant. The exact same thing is true here. All of these indices are contracted. The only new feature is that you have this additional object, which is a Lorentz invariant tensor, just like the Minkowski metric is a Lorentz invariant tensor. So anything that you contract indices using these matrices here is automatically going to be Lorentz invariant. But again, you can go back and check it using these definitions here. Okay. Okay, so that's, I guess, what I wanted to say about spinors. So maybe just in the last few minutes, I can say a little bit about how this generalizes in higher dimensions. Yes, go ahead. Sigma bar in the first term, this term? So the way I wrote it, again, you want the bar here. So the way I'm defining things, which may be not the way you're used to defining things, is that whenever the A and A dot indices are down, I call it Pauli matrix without a bar. If I had put these indices down, then I would have put these indices up, and then I would, so it's related. Okay, you just use epsilons to raise and lower the indices. So there are different ways to write the same thing, but it's the same expression, just using up or down indices. Any other questions? Okay, so the next lecture, what I'll talk about is how to build supersymmetric Lagrangians using this. So of course, you have to combine this with the bosonic, with the Lagrangian for bosonic fields, and we'll see that the supersymmetry transformations of these terms will cancel the supersymmetry transformations of the terms coming from the either scalar or Maxwell field, a photon. So that's what we'll do the next lecture. But just I still have, I think, 3 or 4 minutes. So let me just say a little bit about how you generalize this in higher dimensions, just so you have some idea. Any questions before? Yeah, go ahead. Yes? Okay, good. So I can have more than one spinner, right? So remember, Ricardo in his lecture, he said, well, you can have a scalar, or you could have a complex scalar, which is like phi 1 plus I phi 2. You can do the same for the spinner. So either, instead of just having one chiral spinner, you can have two chiral spinners. So chi is just another spinner. I could have called it psi 1 and psi 2, but I called it psi and chi. So you just have twice as many objects. So a Dirac object you can think of as just being the product of two Majorana. Okay, so at least in the free case, it's the same. But when you do interactions, things are more interesting. So I guess the mass term is more interesting here. But at least the kinetic term is essentially, this is just like the product of two of these. I mean, the sum of two of these. Sorry. Other questions? Okay, so how would you generalize this to higher dimensions? So, so it's easier to talk about in even dimensions. So I'm just going to say this quickly, and I think this part you should understand, but probably the thing I'm going to say quickly just so you have some idea how to do it in higher dimensions. So what you do is you split the D, so you have SO1 D minus 1. I think this is probably not going to make sense to try to do it in 5 minutes. So, okay, I'll just say the answer, and then you can ask questions about it later if you want. So the idea is that you split these into 0, 1, M2, 3, M4, 5, M, D minus 2, D minus 1. So these are a subset of the Lorentz generators. So if you're in D even dimensions, you have D over 2 of these. So these describe, you can think of them as just rotations, certain rotations. And you can ask, what are the charges of the spinner or a general representation under these rotations? So for example, suppose you had a vector. A vector, so for example, in 4 dimensions, you can think of it as if I do a rotation, a boost in the x direction, it has charges essentially equal to 1, 0, plus or minus 1, 0, or 0 plus or minus 1. So you can think of this as a circular, depending if it's polarization, you can just think, so this would be something like A0 plus or minus A1. This would be A2 plus or minus I, A3. So a photon or a vector in 4 dimensions has 4 degrees of freedom. Okay? I'm not talking about physical, we're talking about just how many components the vector has. And we can decompose it in this way, where these components, if I do a boost in the x direction, these will just transform with a certain charge with respect to this boost, which will be plus or minus 1, depending if this is plus or minus. And these will not transform if I do a boost in the, if I do a rotation, for example, in the YZ direction. So they won't transform under this, but they will transform under this. Whereas these, if I do a rotation in the 2, 3 direction, they'll rotate. Okay, so they will have these charges. So you can describe the 4-dimensional vectors in terms of their charges with respect to these, and they're either plus or minus 1. You could do the same thing for the fermions, and you find that in this case it's either plus or minus a half. So this would be the chiral and antichiral fermions, so they can either be plus a half in the, they always have to be plus a half with respect to any rotation. So it can never be 0. It has to be either plus or minus a half. And you see there are 4 different possible combinations, right? Because it would be plus a half, plus a half, plus a half, minus a half, minus a half, plus a half, minus a half, minus a half. So the 4 components, the 2 complex components of psi, or 4 real components, are described by these choices here. Okay? Now this generalizes to any dimension. So for example, suppose you're in 6 dimensions instead of in 4. Then a vector could be plus or minus 1, 0, 0, or 0 plus or minus 1, 0, or 0, 0 plus or minus 1. Those would be the 6 choices of the vector in 6 dimensions. And obviously in 8, okay, you can generalize this. A spinner generalizes this way. So a spinner, if you were in 6 dimensions, so this would be d equals 6, this is d equals 4. You always have this choices here. So for example, a vector always has the same number of components as the dimension. The spinner doesn't. So this, in d equals 4, it's an exception. Here it's 4. And here obviously it's 4 because it's 2 to the d over 2. Right? The number of choices here is 2 to the d over 2, which happens to be 4 in 4 dimensions. But here it happens to be 2 to the 6 over 2 is equal to 8. Okay, so in 6 dimensions, you have different number. So it's always going to be a multiple of 2. So this is true in any even dimension. Okay. Now it turns out you can ask about the reality properties of this. So these are all essentially, this is real, these two are real, and these are the complex conjugates of each other, just because of the signature. You can also ask, how does this, if you do a reality transformation on this, if you do a complex conjugation, how this transforms. And that tells you if the spinner is Majorana. Okay? And vile turns out to be defined by, it's the number of plus signs. So for example, here, in 4 dimensions, you have vile or anti-vile, or chiral or anti-chiral. This would be, the vile could be plus a half, or minus a half, but always an even number of plus signs. Whereas anti-chiral would be plus a half, or minus a half, plus a half. So chiral means that you have an even number of plus signs here. So for example, here you could also ask which are chiral and which are anti-chiral. So these definitions of chiral, anti-chiral generalize in any dimension, and this can be used to, for example, tell you how many degrees of freedom are in the spinner. So just to get an idea how this generalizes in higher dimensions. Okay, so I'll stop now and for questions.
Yeah, we have 10 minutes.
I can repeat the question if you don't want to wait.
Okay, in the board of the right, there is the Klein-Gordon equation.
This one.
Yeah, I
Yes?
think it is the Klein-Gordon equation. The following question is, what implies having the Klein-Gordon equation in that
So Klein-Gordon
of
equation is
motion?
just the name of the equation that tells you that box, which is equal to p squared, or d dx squared with, I guess, with a minus sign, is equal to m squared. So this equation of motion clearly implies that, because if this product is 0 and psi a is not 0, then box has to be equal to m squared, or minus m squared. So that's why this is called Klein-Gordon equation.
Thanks.
Other questions? Some people were asking me about spinners, projective, and stuff. Don't you want to ask?
If you ask them to ask, they will ask.
It's not about that, but it's actually.
You don't need, okay, anyways, I can repeat the question.
I mean, it's not about
No?
the representation, but I mean, I suppose you have a spin 1 massive particle, right? And
Yes.
you're trying to quantize this.
Yes.
You know that it must have like 3 degrees of freedom, right?
Yes?
Sort of the standard. I mean, the way I saw it is you place it inside of a 4 vector, and then you get a Lagrangian that propagates 3 degrees of freedom instead of 1. But why don't we, if that naturally has 3 degrees of freedom, isn't it more natural to just put it in the 1-0 representation? Why don't we do that?
Okay, good. So the problem is that this object here turns out to be complex. So the complex conjugate of this is A dot B dot. So this actually describes an object which you know, but probably you don't know it in this language, which is if you take, for example, antisymmetric 2 form, which like the Lorentz generator, this actually decomposes into, this is not irreducible. So it has 6 components. But it decomposes into itself plus I epsilon. Probably there's a factor of, I don't know, 1 over 4, something like that. So these are also 4 by 4 antisymmetric matrices, but they satisfy this condition that's called self-duality or self-anti-duality, I guess it's called, or anti-self-duality. So this turns out to, let's call this object n, just to give it a different letter, and this would be n bar because of the minus. So this is complex, but it turns out to have a duality property that nmn is equal to, I think, I mn pq, again with some factors of 4 or something like that, npq. So this is called something self-dual, and if there was a minus sign, it would be called anti-self-dual. Now, this, everybody knows, has 6 degrees of freedom. So this has 3 complex degrees of freedom, which are this and these representations are precisely those. So this describes a self-dual tensor, and this describes an anti-self-dual tensor. So if it was real, then what you said might work, but it's not real. So.
Thank you.
Any other questions on this side or on that side? Okay, if not, you can continue to ask Nathan informally. Let me remind you, today we have the dinner at 7 p.m., so people can either leave from here after Juan's talk